One quantity I did talk about in the introduction was this thing known as a critical angle. So if light strikes a material at just the right angle, the light actually runs parallel to the material. And this occurs when the incident angle is what's known as the critical angle, which is labeled here as alpha c. So I actually have the derivation of this formula on the next slide, but the formula for it is that the index of refraction is equal to the cosecant of the critical angle, which is 1 divided by sine of the critical angle. If your calculator has an option to do inverse cosecant, it's fairly straightforward. But if not, it's fine enough just doing 1 over sine of alpha c. So if the incident angle exceeds that of the critical angle, then it just gets reflected back inwards, and it follows laws of reflection. And this process is known as total internal reflection, quite literally meaning that the rays just stay inside of that particular material. So when the incident angle is smaller than the critical angle, then it just gets refracted as per the norm. So how do we prove it? So we know that the index of refraction is sine of alpha I over sine of alpha or. We know that the corresponding refracted angle has to be 90 degrees relative to the normal. So that means when alpha r is 90, sine of alpha r is 1, and so we get n equals sine of alpha I. However, that is actually going the other way round. So it represents going from material B into material A. So as I said, it's going the wrong way around. So a way to sort of circumvent that is by saying that the index of refraction from B to A is the same as 1 divided by the index of refraction from A to B, because they'll essentially cancel each other out. So when we know that alpha r is alpha c, we then just get the index of refraction is just flipping this. You get 1 over sine of alpha c, which is the cosecant of alpha c.